Hi, and welcome to my presentation. I'm Tomy Doda, a PhD student in aquatic physics at Eawag in Switzerland, working in the group of Damien Bouffard, and today I would like to present you some results about density currents induced by differential cooling in a small lake. And I would like to start with this schematic of a mass balance for methane, where you can see all the different fluxes that are affecting biogeochemical compounds in lakes. And one of these flux is lateral transport from the shore, and our project is looking at one specific lateral transport process that could play an important role for biogeochemistry. So what is this process? It's called thermal siphon, and here's a schematic that explains what's happening. So it is driven by surface cooling, which can occur during the night or during cold days. And as a result of this surface cooling, a mixed layer is created close to the surface with this convective motion that you can see here. But a second process is happening at the same time, due to the fact that depth is changing with space. So the littoral region is shallower and it will cool down faster than the pelagic region. So as a result of that, we can get a lateral temperature gradient, which is called differential cooling, with colder water close to the shore. And since colder water is also denser, the littoral waters will tend to plunge as a density current that will intrude at the base of the mixed layer. And this density current is called thermal siphon, and it's the process we are studying. It has been studied in the past, both in the lab and in the field, but we are still lacking of understanding about its seasonal variability. So we would like to predict when it occurs and how strong is the transport in that case. So for that, the hypothesis project has been created and it's led by Damien Bouffard. So my PhD is part of this project. I'm focusing on field measurement, but there are two other parts about modeling. The first one is about 3D numerical modeling, and this is done by Cynthia Ramon. And she's looking at basin-scale consequences of this process. And the second part is LES modeling done by Hugo Ulloa at EPFL. And here we can really look at the small-scale processes and the energetics of the process. Our study site is Lake Rotsee in Switzerland. So it's a small, elongated lake. And we deployed in this lake 2 moorings in 2019, one at the deepest point, MB, and one close to the shore, MT, which is more or less 4 meters deep. Each mooring is composed of a chain of temperature sensors and an ADCP that is measuring current velocity. We also took CTD profiles from time to time, and the mooring remain in the lake for almost a year, and they measure continuously temperature and velocity over that period. So let's see how first a diurnal cycle look like, and this is a simulation done by Hugo. Here you see kinetic energy, so bright color mean fast water motion, and we're going to look at kinetic energy over 1 day. So here you have a schematic showing you the sun. So we start the simulation at the middle of the day and we go towards the night and the cooling period. And we're going to look mostly at what's happening close to the shore. So let's see. At the beginning, we can already see surface cooling happening with these convective plumes close to the surface. And at the end of the night, we start to see a process here, so a flushing of the littoral region, which is the thermal siphon that I was mentioning. And you can see that this process is still happening during the day, and that we have to wait until half the day to have a weakening of the process. So we see that thermal siphon is driven by differential cooling during the night, but it's happening with some inertia and it's still present during the next day. So let's see if we observe something similar in the field now. Here is, you can see the temperature as a function of the distance from the shore, so going from that point to the middle of the lake. And this has been extracted from CTD profiles. Each line is a profile, and it has been linearly interpolated. So you can clearly see here that differential cooling was taking place with colder water close to the shore. And we can also observe that the isotherms are following the sediment, here indicating cold water flowing down and intruding at the base of the mixed layer. So let's look now at the velocity, and here we're going to look at the velocity over 1 day, and we're going to focus on cross-shore velocity. So red positive values mean water moving offshore, blue negative values mean water moving towards the shore. And here the measurements were taken at MT. So let's look at the night first. Here the lines are isotherms, 0.01 degree isotherms, and you can see that during the night we have a well-mixed water column with vertical isotherms, and at the same time we can see that there is a positive cross-shore flow that is happening as pulses, and this is likely due to convective plumes. Then, during the next day, this is when we start to really observe the thermal siphon, so you can see a clear flushing which is over the bottom 1.5 meters or so, and which can reach velocity of a few centimeters per second. And you can see that this flushing is matching with the isotherms, so the isotherms are parallel, indicating that it's cold water that is flowing down. And it's lasting for some hours until the beginning of the afternoon, so we can clearly see the inertia I was mentioning before. Of course, this is one specific day, but we observe the same process many days, and here is an estimation of the percentage of days when this thermal siphon occurs. And you can see that in summer and fall, it's present quite often, actually more than 80% of all the days we measured in late fall. So I'm going to focus just on that period now, and I would like to compare our results with lab experiments that were done in the past, where this scaling formula has been found for the velocity. So it relates the cross-shore velocity with the surface buoyancy flux, which is an indicator of the strength of the cooling, and a horizontal length scale, which is the length scale of the littoral region here that could be defined based on the mixed layer depth. So based on our measurement, this is a measurement from summer and fall, you can see that we also got a linear relationship of the same type with a slope parameter that is on the same order of magnitude than the parameter found in the lab. So it's quite consistent. And now I would like to finish a bit by showing you the Basin-scale effects, because here we just focus on one specific point in the lake, but how does the process occur over a larger scale? And for that, we need modeling. So this is a result got by Cynthia. She performed a numerical tracer experiment. So she injected a tracer all over the lake in the littoral region, and we're going to look at the transport of the tracer during the night. So here we go. You can see that it is transported all over the lake. It is stronger, the transport is stronger for the two shallow regions at the lake edges, but it's still occurring even in the steep region. And Cynthia estimated that after 6 hours, 80% of the littoral region is flushed. So it's really an effective flushing process. So to conclude, we can say that the process is significant. It has a velocity of a few centimeters per second, a few meters fixed, and it can flush the littoral region in a few hours only. It occurs with some inertia, and it occurs mostly in summer and in fall. And we saw that its current speed can be linked with forcing condition and stratification. Here are the different references I used in my presentation. And with that, I would like to thank you for your attention and to thank all the people who helped me in the field and who gave me feedback. So if you have any question, please leave a comment here or join the chat on Monday, or you can also contact me.